Now that we have defined the basic operations that we can perform on vectors, we're poised to make the tie between our discussion on geometry and our definition of linear systems. So we're going to start out with the definition of a linear combination. The linear combination of the vectors v1, v2, down to vn, which are all m-dimensional vectors, and the n scalars, c1, c2, down to cn, which are just real numbers, is the m-dimensional vector c1, v1, plus c2, v2, plus etc., plus cn, vn. The scalars c1 through cn are called the weights of the linear combination. To make geometric sense of this definition, we once again appeal to our simple two-dimensional game. We used two special directions, E1 and E2. We identify E1 with the unit vector in the positive x direction, and E2, the unit vector in the positive y direction. So starting from the origin, to locate the tip of the vector v, which is x is its x-coordinate, y and its y-coordinate, which we can express as x times E1 plus y times E2, we made rectangular moves through R2 using the weights x and y, identifying the number of horizontal steps and vertical steps, respectively, that we needed to take to locate that point. Through this lens, we can generalize the game to m dimensions as follows. The choice of vectors v1 through vn can be thought of as a set of rules that specify how you are allowed to move through m-dimensional space. That is to say, the linear combination c1v1 plus c2v2 plus plus cnvn is the set of instructions: walk c1 units along v1, walk c2 units along v2, etc., until finally you walk cn units along vn. Now, of course, being a game, our game should have a goal. And the goal is to answer the following question. Given any point in Rm, can we move from the origin to that point using only these directions? In our new language, which is to say, suppose we are given the vectors v1, v2 through vn, which are all m-dimensional vectors. We could actually formulate an equivalent question. Given any m-dimensional vector, b, can we find weights c1 through cn such that b can be expressed as c1v1 plus c2v2 plus plus cnvn? While this question may seem daunting at first, we can see that it is a tractable problem by looking at an example in R2. Suppose we choose the two vectors v1, which is root 2 over 2, root 2 over 2, and v2, which is root 2 over 2, negative root 2 over 2. If we think about this geometrically for a minute, we recognize that these are both unit vectors. To translate this back to our game, we use these two vectors as our only allowable movements in the game. And they correspond to the point on the unit circle at pi over 4 and the point on the unit circle at minus pi over 4 radians, respectively. Effectively, we've simply taken our game and rotated it. So instead of standing at the center of the room and looking directly at one of the walls, now you stand at the center of the room and look at one of the corners. You can still only move forwards and backwards, left and right, as long as you're looking at the corner of the room. Intuitively, we should believe that we can still reach all of the same points as before. To make this more precise, suppose that we have a vector b. Its coordinates are b1 and b2. Whether we can reach this point using a combination of moves along v1 and v2 depends entirely on whether we can find weights so that C1V1 plus C2V2 is equal to B. If we write these down as an array of numbers, then we get the following equation. In order for these two vectors to be the same vector, they need to have exactly the same coordinates. To solve for the weights, we need to find C1 and C2 that therefore satisfy the two equations, but this is exactly a system of two equations and two unknowns. So the answer to our question lies entirely in the consistency of a linear system. For a small system like this, it's easy to find the general solution. Multiplying row 1 and row 2 by 2, we get. Next, we can subtract row 1 from row 2. Then we can scale row 2 by a half. Next, we can add row 1 and row 2. And finally, we can scale row 1 by 1 over root 2, scale row 2 by negative 1 over root 2. And this tells us that our solution is given by taking the weights to be C1 is B1 plus B2 over root 2. C2 is B1 minus B2 over root 2. C1, so for example, if you wanted to reach the vector E1, the coordinates of E1 are 1 and 0. So we can write E1 as 1 plus 0 over root 2 times V1 plus 1 minus 0 over root 2 V2, which is the same thing as 1 over root 2 V1 plus 1 over root 2 V2. Now, as before, we can generalize this example to arbitrary vectors in Rm. So suppose that we are given n vectors vi, whose coordinates are v sub 1 comma I through v sub m comma I, where I ranges between 1 and n. And we're given a vector b, whose coordinates are b1 through bm. We use the shorthand v1, v2, vn with the augmentation b to represent the m by n linear system, which we have expressed as an augmented matrix whose columns are v1 through vn. Now, to tie the system to the linear combination, we make the following observation. In our new language, if we are given vectors v1 through vn of dimension m, and a vector b also of dimension m, there exist weights c1 through cn such that c1v1 plus blah 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 plus cnvn equals b, if and only if the m by n linear system, which we represent as the matrix, the augmented matrix, with columns v1 through vn and b in the augmentation column, is consistent. In particular, the weights are precisely the solutions to the linear system. So this is our tie-in to a geometric understanding of space through linear combinations and an algebraic understanding through systems and augmented matrices. This is a relationship that we are going to use and exploit time and time again throughout this course.